Just preparing, setting up your meeting for YouTube Live. Done. Redirecting to YouTube. We're good to go.
All right. Hello, everyone. Apologies for the slight delay. We had some technical issue. Thank you for joining us for May's EPSP Connect seminar. Just a brief reminder that the purpose of this seminar series is to bring together the community and to help establish connection between people who might not be able to interact with others in different settings. And so we are very, very happy to have you here. I would like to thank all of the EPSP Connect team members that helped and plan this series, and reach out to potential speakers and coordinate with them, and who advertise in social media and make sure that the series information is up to date on the website. Together with me today as a co-host is Shashank Anand, who will help us with the Q&A session at the end. So Shashank, please tell us what's going to happen after the presentation.
Thanks, Elvise, and hi everyone. This is Shashank. Generally, we allow all the questions to be posted as they come. So if you have a question on a slide, please feel to post it and we'll monitor them. And those who want to ask the question directly, at the very end, we can ask you to unmute and you can ask the question directly. For the people who are joining us from live stream on YouTube, we'll also keep an eye out on it for questions.
All right, thank you. And our today's speaker is Dr. Roland van de Wijzel from Wageningen University in the Netherlands. And I'm very happy to be hosting him. Roland has just recently started as the new track assistant professor at Wageningen. He's a physicist by training, but he's long ago joined the dark side of the force, so is now working on hydrological and geomorphological issues, as you might say nowadays, when you're going to talk about nonlinear dynamics in river tide and wave-dominated ecosystem. So, Roland, please, the stage is yours.
Thank you, Avisa. Hi, everyone. Good afternoon, good morning, or good evening, depending on where you are. Firstly, my sincere apologies for the delay. I had some technical issues, but I'm glad that we got it all running in the end. So just to check, you can still hear me well?
Yeah.
Perfect. Okay, thanks. So today I'll be talking, as Avisa already introduced, about nonlinear dynamics that can happen in both river, tide, and wave-dominated systems. On the background, you can see an aerial image of the Scheldt estuary on the border between the Netherlands and Belgium. And this is part of the larger Rhine-Meuse and Scheldt Delta. You can already see some interesting features here. You see, of course, this very large tidal wetland, which is the drowned land of Saftingen. You can see tidal flats. You can also see that this area is very densely populated. So you can see the harbor of Antwerp on the background. You can see a nuclear power plant. So you can already imagine that it's very important to understand all the morphodynamics, hydrodynamics that are going on in this area. Next slide, please. Or can I also click myself? No. No, you're right. So just a very brief background. As Avisa already introduced, I have actually a background in physics, studied in Utrecht in the Netherlands. And then I did my PhD at the Royal Netherlands Institute for Sea Research in this beautiful delta area of that country. Then I went to Spain to study seagrass meadows. I'll show a bit more about that later. I worked at IFISC, which is the Institute for Cross-Disciplinary Physics and Complex Systems on the beautiful island of Mallorca. And then I came back to the Netherlands, where I am working now as well. First as a postdoc, and since March as an assistant professor. And recently I've also been collaborating with people from Woods Hole Oceanographic Institution and the USGS in Woods Hole. Next slide, please. So why do we actually care about nonlinear dynamics that I mentioned in the introduction slide? Well, many of you may have seen in the news, news about tipping points or large collapse that can happen, for example, in biodiversity. Next, please. But also in the climate system, we have these very large scale sudden changes that can happen. For example, now the idea is that the AMOC, Atlantic Meridional Overturning Circulation, could suddenly shut down. Also think about ice sheets that could melt irreversibly. Next slide. But also in biogeomorphology, morphology, we know that there are tipping points. So for example, tidal marshes, salt marshes that could suddenly drown due to sea level rise. Next, please. So just for those of you who are not so familiar with the idea of tipping points or nonlinear dynamics, just a brief overview of what I mean with that. So on the left, you can see a very idealized way to represent this tipping point in tidal marshes. So normally tidal marshes, they can keep up with sea level rise as long as they have enough sediment supply. But if either sea level rises too fast or sediment supply is limited, those marshes may drown. And this drowning is not, as you can see on the right panel, just a simple, it's not just a simple linear loss of, for example, vegetation biomass with increasing sea level, for example, but instead, next please, due to inherent feedbacks in the system, this response is nonlinear. And next, if these feedbacks become even stronger, this nonlinearity can result in different stable states that can coexist under the same conditions. So these stable states are here indicated by solid lines, and the dashed line indicates an unstable steady state. And next, you can imagine that once the system moves beyond a threshold, so a critical rate of sea level rise, then the system could very rapidly drop to a contrasting state. In this case, a system without a marsh. Next, please. And also large disturbances such as hurricanes, they can potentially tip a wetland system to a different state already before this theoretical tipping point has been reached. Next, please. But, well, the reverse is maybe also possible, and I'll touch upon this later. Potentially, we are also able to tip back a degraded system to a more favorable state. Next, please. And eventually, we would like to develop what we call resilience indicators, so indicators that tell you how robust or how vulnerable a system is to tipping. Next, please. Now, a lot of research has already been done on those so-called resilience indicators. Recently, we wrote a review paper kind of summarizing all these kinds of indicators. I'll not go into all this detail yet. Next. But for now, I'll focus on 3 key concepts. Next, please. Which is, well, firstly, you can imagine, well, I show these bifurcation diagram, so this S-curve, but you can also represent it as follows. So here you can see so-called stability landscapes. So this valley is the stability landscape, and the ball is the state of a system. And you can imagine that if the ball is in a valley, it's a stable state, and if it's on top of a hill, it's an unstable state. And you can imagine that if a system becomes closer and closer to a tipping point, we say that it loses its resilience. And you can actually measure this in time series, because the closer you get to a tipping point, the shallower this valley becomes. And as a result, the slower a system will respond to perturbations. And this is known as critical slowing down. So that's one key concept. And the next slide, please. Next topic I will be talking about is known as flickering. And the idea behind this is that due to inherent stochasticity in the system will always oscillate around its stable state. But when the system enters a regime where you can have these 2 stable states coexisting, the system will start to flicker, we call, or switch back and forth between these 2 possible stable states. And you can actually measure this in the frequency distribution of your observations, and you can translate this back into this stability landscape. Next, please. And a third concept I'll be talking about is the effect of spatial self-organization or spatial pattern formation. because we know that once these patterns, when a system, instead of just being spatially homogeneous, when it develops these spatial patterns, we know that this patterning is a way for the system to kind of avoid a very drastic shift and instead go from one state to the other in a more gradual way. Next, please. So today I'll be talking, well, first about which of these systems focusing on river deltas actually do exhibit tipping points and where in the world are they most vulnerable. Then I'll look at two examples of how we can actually predict or anticipate such regime shifts, if we can avoid them happening, and finally, if we can also tip back degraded systems to more favorable states. Next, please. Yeah. So, yes, next, please. So we know, of course, for deltas, river deltas around the world, there are physical boundary conditions. So, for example, sediment supply is hampered due to anthropogenic forcing. Next, please. Also, well, many hydrodynamic forcing factors are changing. Next. So yeah, of course, sea level rise. We know that storm surges are becoming more stronger. River floods are becoming stronger. Next, please. Relative sea level rise is a threat. Next, please. And well, for river deltas around the world, all of these changing boundary conditions are important. Every river delta has a different combination of changing factors, but we saw that basically for all of the major river deltas around the world, at least one of those boundary conditions is changing rapidly. Next, please. And so we concluded, well, if those boundary conditions are changing so rapidly, this probably also has implications for the likelihood of tipping points occurring. So in this review paper, we discussed, well, we grouped all possible kinds of tipping points into three categories. So changes in channel stability, changes in turbidity regime in estuaries, and changes in coastal wetlands. Next, please. Next. So just to give you an idea of coastal wetland changes, I already introduced it in the beginning. So think about large-scale marsh loss, for example, as is happening in the Mississippi Delta at the moment. Next, please. Next. So if you think of changes in channel stability, you could think of large-scale bank retreat, bank failure. That's another, well, an example of a critical point that's being passed and a regime shift that follows. Next, please. But next, you can also think of changes in turbidity in estuaries. So, for example, in the Ems estuary on the border between the Netherlands and Germany, this estuary has been deepened over time to allow bigger and bigger ships to pass, as you can see on this picture. And as a result, the tidal signal has become more and more flood dominant. So the flood wave in this estuary has become stronger. This has led to a gradual import of fine sediments, which kind of smoothens the estuarine bed. And this reinforces the strength of this tidal flood wave. And because of that, you get even more fine sediments that are being imported. And this runaway feedback has caused this estuary to become very, very turbid. Next, please. So, okay, knowing about all these kinds of regime shifts or tipping points that can occur in these coastal and deltaic areas, can we actually predict or anticipate when they might happen? So as a first example, I would like to zoom in again on tidal marshes. Next, please. Specifically on the Mississippi Delta. So this is work I've done with colleagues of Wageningen, Woodsell Oceanographic Institution, and the USGS. Specifically, we want to know, next please, how vulnerable these marshes are to the frequent hurricanes that are passing by in this region. Next. Specifically, Hurricane Katrina, of course, which you all are familiar with, that passed by in 2005 and was exceptionally strong. Now, we see already in observational data that large portions of this tidal marsh have disappeared over the past, say, 20, 25 years, as you can see in the red pixels in this aerial image. Next. For now, I'll actually focus on this region over there. Next, please. And so we want to know, can we predict when these marshes are most likely to drown, to disappear, because a tipping point has been exceeded? And again, I would like to come back to this idea of critical slowing down that I introduced in the beginning. So the system responding more and more slowly from perturbations as it gets closer to a tipping point. Next, please. So this idea actually has already been proven to work for tidal marshes. So in another study, they measured for each point on a marsh how long that patch of vegetation took after a disturbance to recover. And this recovery time is expected to slow down when you get closer and closer to a tipping point. Next, please. But we wanted to know, can you also apply this to a system that's much more vulnerable to very large disturbances such as hurricanes? So we wanted to test the same idea with satellite data in the Mississippi Delta. Next, please. So first, we zoomed in again on this region where we know already that a lot of marsh has lost. Next, please. And then we selected, well, to start 3 points on the marsh, A, B, C. Next, please. And we looked at time series of the NDVI, so the health of vegetation. And you can see for point A, that's relatively high up on the marsh. After Hurricane Katrina, which happened in 2005, nothing happened much. So the seasonal cycle of NDVI just basically continued how it was. But if you look at point B, which is a bit lower on the marsh, you can already see some disturbance after 2005, but then the marsh seems to recover again to the seasonal signal. But point C, which is much lower on the marsh, really seems to be impacted by Hurricane Katrina. So it's disturbed and it doesn't recover. So that already supports this idea of critical slowing down that we have. Next, please. And we actually quantified this recovery time more robustly for all points on the marsh. And then if you plot that, you get a map like this, where blue means low recovery rate or low resilience, and yellow means high resilience. Next, please. And if you compare this with the actual observed loss, you can already see that most loss seems to have occurred in these very dark blue areas, so in these regions of low resilience. So that shows that this idea of critical slowing down indeed could be applied also on this much larger spatial scale and in systems that are very vulnerable to very large disturbances. This is still work in progress, and hope to update you on that soon. Next, please. So another system is actually, instead of tidal marshes, river-dominated systems, specifically bed forms that you can have in rivers. Next, please. So as many of you may be familiar, many rivers show these very large bed forms, so large, say, waves on their bed. You can see that very nicely in this picture that was taken during an extreme drought in the Paraná River in Argentina. You can see these bed forms are very large, meters in length, and half a meter to maybe a meter or more in height as well. And what we found in this research that has just been accepted is that when flow speeds become very large, then the system seems to switch back and forth between alternative stable states. Next, please. So for those of you who are familiar or who are not so familiar with dunes, typically what is known is that when flow speeds increase, then you go from a flat riverbed to small bed forms, ripples. Those ripples can grow when the flow speed increases to dunes. But then when flow speeds increase more and more, these dunes start to flatten out, and eventually you can go to a upper stage plain bed again. Next, please. But what my colleague Jacques Lange found in previous lab work is that there seems to be something off there. So next, please. As you show indeed that under low flow speeds, in these bed scans that were taken in a lab, in a flume setup in Wageningen, under low flow speeds, indeed the dunes or the bed forms were very small. The flow speeds increased, those bed forms started to increase in size as expected. Next, please. But then under very high flow speeds, something weird seemed to happen. So in some flume runs, you can see very large dunes. In other flume runs, under relatively comparable conditions, the bed is suddenly flat again. So this very strong variability in the outcome under high flow conditions was something we didn't understand. Next, please. So we dove into literature, dove into what has been done by previous authors, and we plotted dune heights, here indicated by delta, as a function of time for 3 different flow speeds. So here, theta over theta c is the transport stage, and that is a measure of flow speed. So you can see in panel A, just lone dunes fluctuating a little bit over time. But as flow speeds increase, so panel B and C, you can see larger dune heights, but also much larger fluctuations over time. When we plotted again dune heights as a function of this transport stage, as a function of flow speed in panel D, you can also see by the size of the error bars that this variability in dune morphology very strongly increases with increasing flow speeds. Next, please. So to understand this better, we analyze this data better. On the left, you can see the actual variability in dune heights, again, as a function of the transport stage. And you can see this almost linear increase in variability. And specifically, we saw when we plotted frequency distributions of dune height for each of those transport stages, we saw that at some point, those frequency distributions started to become bimodal. And you can see that in the right panel, where we measured the distance between the 2 modes that we observed in frequency distributions. And you can see in this panel that the stronger the flow becomes, the higher the transport stage, the more separated these 2 modes become. So the frequency distributions really become very bimodal. Next, please. And we also tested this in our own experiments. So over here you can see an XT diagram, so space-time diagram of flume run we did. So along the vertical axis you see time in minutes. Each panel, each next sub-panel continues where the previous one ended. And along the horizontal axis, along the x-axis, you can see the location along the flume, so in the flow direction. You can see by these diagonal lines, you can see that dunes are migrating through the flume. And you can see in those panels this alternation between sometimes very narrow and low dunes and sometimes very wide dunes. And this is indeed that same sort of oscillating back and forth between high and low dunes that we also observed in previous literature. So our own flume runs supported what we saw in previous literature. Next slide, please. And the hypothesis that we have for why this occurs, this large variability in dune height, is that a tipping point has been exceeded. So over here you see a very simple, very simplistic way to represent that. So you can see again a stability diagram as I indicated in the beginning. So solid lines mean stable states, and the dashed line is an unstable state. And you can see here, a response variable, for example, dune height, is a function of a controlling variable such as transport stage. Next slide, please. And when we simulated how the observed dune height would fluctuate in a more stochastically influenced environment, how it would fluctuate around this stable state, we saw indeed in the simulations that, say on the left half of the panel where you have only one stable state, the system or dune heights will fluctuate around that one stable state. But then once you exceed this tipping point, roughly halfway, the system will be able to switch between those 2 alternative stable states. Next, please. Next, please. And you can actually also quantify this again in these frequency distributions, as I mentioned in the beginning. So on the left, so before the tipping point, the observations are unimodally distributed, but once you exceed this tipping point and you have alternative stable states, you will also see this back in a bistable frequency distribution. So we think that this can explain, or at least this very simplistic model, is what could have happened in our observations. Next, please. So as we speak, actually, we're setting up follow-up experiments where we also want to understand better what the physical mechanisms are behind this, this possible flickering between alternative states. Next, please. But anyhow, irrespective of the exact mechanism, this finding has important implications, because if, especially during those high flows, if it's not so certain if you will have dunes or if you will have a flat bed, this has a very strong implication for influence on the roughness that these bed forms create, and as a result also on inundation heights during floods. So with dunes, with bed forms present, typically the flow is slowed down, and as a result, your flood height is much higher. So we really need to understand what's happening here. Next, please. And also, well, just like what's already being done in ecology, typically, we really need to also do replicate experiments in morphology. And I think this is also something that's not that typically done in our field, because we assume that, well, you can just do one flume run and that gives you the outcome. But our findings suggest that it's really important to do these replicate measurements also. Next, please. So then the next question is, okay, knowing that these tipping points exist or these regime shifts can occur, can we do something to avoid such critical shifts? Now, firstly, I would like to move to a wave-dominated system. Next, please. Specifically, this beautiful bay in Spain around Mallorca. Next, please. You can see in the overview map where that is. Next, please. So if you look beneath the waves, you can see in this habitat map, there's a lot of seagrass present. So that's this dark green color. Yellow is just bare sand. And you can already see that the seagrass meadow is not just a uniform cover, but you can see all those little yellow specks, which are all large holes or larger gaps in the seagrass meadow. That's quite significant. So these gaps can be spaced around 50 to 60 meters apart and be several meters in diameter themselves. And we wanted to understand what creates this gap pattern. Next, please. And what we found, or what we hypothesize, is that these gap patterns are formed due to wave reflection. Oh, I think it's already. Can you press next? So what we so there's this phenomenon known as Bragg reflection, which means that when water waves, ocean waves, when they travel over a seabed that itself has, say, a wavy pattern, so has large bed ripples, we know from theory that the incoming ocean wave can be reflected. And this is first what we demonstrated in this simple hydrodynamic model. Can you press next, please? So you can see in the simulation on the top panel, you can see wave heights. Well, blue indicates the wave traveling to the right, and red is a wave that's being reflected due to this effect of Bragg reflection. And then the second and the third panel actually give the flow speeds related to this incoming and this reflected wave. And we think that this effect of waves reflecting over wavy surfaces, this Bragg reflection, could explain the observed seagrass patterns. Next, please. So to test this, we developed another model where we actually incorporated the coupling between waves, which create a bed shear stress pattern, so a pattern of erosion and deposition on the seagrass on the ocean bed. We know that more bed shear stress can lead to more mortality of the seagrass, and then we also know that where seagrass grows, typically the bed is more stable, and as a result, you have more sedimentation. So in the end, the effect of sedimentation and erosion feeds back again on wave reflection or on wave propagation via this Bragg reflection ID. Next, please. And so we tested this we implemented these feedbacks in a model, and you can see here the top panel is again in blue wave heights of incoming waves, and in red reflected wave. The middle panel in the black lines, you can see the resulting bed shear stress pattern, and in the bottom panel in green, you can see the resulting pattern in seagrass and also in morphology. And you can see that indeed, starting from just a flat bed with some random perturbations, this idea of wave reflection can create a self-organized seagrass pattern. So we conclude from that by forming these self-organized patterns, so these gap patterns that we see around Mallorca, for example, the seagrass meadow is actually able to reflect more of the incoming wave energy. And this may be, well, maybe an evolutionary mechanism. So by forming these spatial patterns, the ecosystem, the seagrass ecosystem, is more able to protect itself from hydrodynamic stressors. Next, please. And then following up on this idea of self-organization as a way to kind of avoid stress or avoid negative impacts by physical forcing, we also looked at tidal marshes. Next, please. You're probably familiar with these very beautiful branching channel networks that you can see in tidal marshes, which, for example, here in Saftingen, again, close to the harbor of Antwerp. Next, please. So we know that so-called scale-dependent feedbacks are acting in these tidal wetlands. So on the left, you can see the feedbacks if no vegetation would be present, where locally, if the seabed or the sediment bed is slightly higher, this causes the tidal flow to kind of move around this obstacle and scour more around this obstacle. And this is a self-reinforcing feedback, because once the tidal flow starts to scour a little bit more around this obstacle, then this becomes a lower area and it attracts more and more flow. So this channelization feedback can already explain the formation of channel networks without the presence of any vegetation. But what we also know is that vegetation, as you can see on the right panel, actually reinforces this feedback, because when vegetation grows, typically on higher elevation, it causes much more scour, because it locally decelerates the flow and actually makes the flow accelerate around vegetation patches into the nearby channels. So we know that this so-called scale-dependent feedback is present without vegetation, but vegetation strongly amplifies it. Next, please. And we can see that also back in models. So we developed a very simple model to show how these channel patterns are being formed. So you will see on the top two panels, say topography and vegetation presence, and in the lower panel you'll see the flow pattern. Can you click, please? So without vegetation on the left, you can see branching channel network that forms, but if vegetation is present, as on the right, you can see that this channel network becomes much more intricate, so much more complexly branching, as we also see in the field. And this is purely due to those scale-dependent feedbacks that are stronger when vegetation is present. Next, please. Next slide, I think. Yeah, thanks. And we know that the effect of vegetation on channel network complexity also has very important implications for the functioning of this ecosystem. So when we simulate channel network formation with increasing feedback, say biogeomorphic feedback strength, so going from the left to the right, well, you can see that the channel network becomes more and more spatially complex, so more branching. And we see that as a result of that, as you can see in the lower panel, sediment accretion rates increase, but also the drainage density, so the amount of, or the efficiency of drainage of this network increases. And that's very important, because that means that when the channel network is more complex, this ecosystem is also better able to get rid of the water after inundation. That's especially important with rising sea levels, of course. Next, please. And also what we found in a follow-up study is that these more complexly branching networks, they cause more sediment supply to the marsh. So we saw that both in model simulations and in field observations, that because of this flow confinement in the channels next to vegetation, because of this confinement, the flow speeds are higher, and this allows sediment to be transported further onto the marsh. So in other words, these spatial patterns, so both patterns in seagrass meadows that I showed before, but also in tidal marshes, they are really important for these ecosystems to be more resilient to to stronger tidal or stronger physical forcings, and thereby allow them possibly to avoid tipping to a degraded state. Next slide, please. And then finally, I would like to end with a bit of a hopeful note. Of course, I've been talking a lot about tipping points, ecosystem collapse, which is not per se very positive. But I think that the positive thing about the presence of these tipping points is also that theoretically we would be able to tip back a system that's degraded. Next, please. And I'll show an example again from these very turbid, these hyperturbid estuaries, such as the Ems estuary. Now you can see on this image a storm surge barrier. And the idea is now that we could potentially use this storm surge barrier to reverse this feedback cycle that caused the system to become hyperturbid in the first place. Next, please. And the idea is that if you open and close the storm surge barrier repeatedly during tidal cycles, you are able to steer the tidal wave to make the tidal wave less flood dominant and more ebb dominant. And as a result, you would be able to cause a flushing out of this fine sediment concentration. And once you are able to flush out these fine sediments, you can imagine that also this feedback cycle will reverse again. So less fine sediment, so the riverbed becomes rougher again, which further decreases or slows down the flood tide. And eventually you might be able to really flush out this very high turbidity. And well, people in the water board in Germany that operates this storm surge barrier is actually already testing or has been testing this idea. And so far the tests are, how do you say? Well, they seem promising. So after several repeated openings and closures of this barrier, you really see that the estuarine turbidity has dropped a lot. So I think this hopefully allows us to end on a more positive note with the idea like, okay, we know that there are tipping points that can cause large-scale negative regime shifts in river deltas, but knowing how these feedbacks work, we are possibly also able to reverse them and let nature actually use those same feedbacks to rapidly shift back a system to a more favorable state again. Next, please. And with that, I would like to thank you very much for your attention and be happy to take any questions.
Right. Thank you very much, Roland, for the excellent talk. I'm gonna give it to Shashan and see if there's any question.
Yeah, actually, we do have a question, and in the meanwhile, please feel to post your questions. So it's from Dendre, and he's asking, do you consider the flickering between steady states, that is, dunes under high flow, to be low resilient or a high resilient system?
Yeah, thank you. That's indeed a very interesting question. So the short answer is we don't know yet. If you would think about flickering in ecosystems, such as, for example, marshes or seagrasses, you would say that flickering means the system is approaching a tipping point, right? So it becomes less resilient. It's say becomes possible for an established marsh, for example, to suddenly disappear. But I think in the case of riverbed forms, it's slightly different because a system without dunes is not per se a degraded state for us, right? Actually, a system without dunes under these very high flow conditions will probably have a higher transport cap or have a higher conveyance, so the water will be able to flow more easily out of the river. And if you think about flood risk, this is actually beneficial. It's actually beneficial to have no dunes under these high flow conditions. So the idea of resilience, or say positive or negative, is a bit different, I think, then. So indeed a very interesting question, and yeah, we don't know the real answer yet, I think. I hope that answers your question.
Well, I can relate to the last part of Roland reply, I guess, related to like the dune presence at flooding risk. How do you, I mean, is there a way in which you can predict which state is more likely to occur, like dunes versus no dunes? And what would be your recommendation if you are like, I don't know, in charge of advising managers, like, what to do in terms of like ensuring flooding risk safety?
Yeah, so at the moment, I think we are not really able to predict if you will have dunes or not. As I showed in one of the slides, typically we now use this parabolic dune height predictor, which is a purely empirical relation that predicts, okay, when flow speeds become higher than a certain value, dune heights will decrease again, eventually to this flat bed. And even though we see this large scatter in our observations, we still use this, say, the same predictor that just implies there's only one possible outcome at high flow speeds. So I think we need to also modify our current theory or our theoretical understanding. Partly by doing, of course, observational work in the flume, for example, but I think also with modeling. As far as I know, at the moment, there have not been modeling efforts yet that have shown this flickering behavior. So I think trying to reproduce that in a physics-based model is also one of the first steps again towards predicting.
Yeah, having a mobile bed in a classic hydrodynamic model is already a big step. So yeah.
Yeah. No, it is definitely. Yeah.
We do have a question actually from Wout. It says, if I'm not mistaken, all examples of flickering you showed were from field or experimental observations. How would you modify existing models to include this flickering behavior, which I think kind of goes back to what we are discussing right now?
Yeah. Well, I think you can start with you have, of course, different types of models, right? You have the models that really represent the whole hydrodynamic, depth resolving hydrodynamics, sediment transport, but you also have stability models just show if dunes grow or decay. I think you can start with these very simple models to see do the stability models support the idea of two stable states that can coexist under high flow conditions. And if they do, then try to also reproduce this in more sophisticated models. Yeah, so I'm not sure yet what is missing now in the models yet, why this hasn't been seen yet. If it's, I can imagine that say stochasticity is important, because these random events, those are what actually kind of push the system to either of the two stable states. So possibly in our simulations we yeah, we don't let stochasticity play a large enough role. That could be. Mm,
I kind
hope
of
that
agree.
Sorry?
I kind of agree with that. Especially when it comes to sediment transport, it's all like, sort
Yeah.
of treated in mechanistic ways.
Yeah, definitely.
All right. Well, Shashank, I don't know if you are monitoring YouTube as well and if there are any questions in there.
I'm
we're live on
watching
YouTube.
it. There are no questions on the YouTube channel.
All right. Well, I guess then we can try and wrap it up. So we're gonna stay on the time schedule we set at the beginning, which was 1 hour. So thanks again, Roland, for sharing this part of your research with us.
You're
We of
welcome.
course
Yeah.
look forward to other research output, and we would be keen to continue learning about nonlinear dynamics. And thanks, of course, to everyone that joined us today. Just a brief reminder to the attendants that there's going to be no seminar next month because the EPSP seminar is going to be on summer break. All right, but keep looking at our webpage to be updated on the upcoming seminar and initiative from the EPSP Connect committee. All right, thank you again and enjoy your
Thanks
day
a lot.
or evening.
Bye.